So now we're going to look at the Doppler effect. Now when you hear a sound, you usually assume that the frequency that you are receiving at your ears is the same as the frequency that's emitted by the source. That's kind of shown in this picture here, that you as the detector are receiving the same wave that is given off by the source S. Surprise, surprise, that is not always the case. The Doppler effect happens when either the observer, the person receiving the wave, in this case sound, moves towards the source, or if the source that's creating the sound or generating that sound just happens to be moving towards the observer. By definition, the Doppler effect is an observed increase or decrease in frequency due to relative movement between source and observer. And here you have an exact definition. Let's have a listen to what that sounds like. I think YouTube has a nice little sound effect which we can listen to. And as you can hear, the pitch changes as the object moves away. Let's look more closely at how the pitch changes with relation to the relative movement of the observer and the source. If we look at what happens when the source moves closer to the observer, we can see that the sound waves, which are normally dissipating uniformly, they kind of get squashed together as the source moves towards the observer, as it tries to literally overlap with them. And that kind of movement forward causes a scrunching up, a kind of squashing of the outgoing waves. So the actual effect is that you get a shortened wavelength. That shortened wavelength causes a higher pitch or frequency. Similarly, if your source is moving away from the observer, then what you end up with is a kind of stretching out of that wavelength. As the waves separate, they continue or tend towards the motion of the object. So what you end up with is a sound which is lower in frequency. You have a lower pitch as the object moves away. Now this phenomena is also apparent when it's not the object that's moving, but it's actually the observer that's moving. So let's have a look at that a little bit more closely. As the observer moves towards the source, then what happens is if you imagine yourselves as the observer, you would be receiving each wave crest in a shorter and shorter amount of time. So it would be almost as if you were squashing that wave as well. As you move towards the source, you would end up having a higher frequency as you move towards it. And as you move away from it, okay, so if you were here and you were moving away, it would take longer and longer for each wave crest to reach you then. So what you would have there is almost like a spreading out of the wave, and that would be a lower frequency. So let me sum that up. So as D, the observer, moves away from the source, you would get a spreading out and a lower frequency, and a spreading out of that wavelength. As the observer moves towards S, then you would end up with a higher frequency because you would be meeting those waves quicker and faster, causing a smaller wavelength and a higher frequency. As S, the source, moves towards the observer, exactly the same situation, you would get a higher frequency. And as the source moves away from the observer, you would end up again spreading out the wave and getting a lower frequency. Now there are two relationships for this Doppler effect, one for each situation. The first situation here for this relationship is when the source moves towards or away from the observer. We'll break that down in a second. The second situation, where the velocities are on the top, are for when the observer is moving towards or away from the source. Now, as you note here, there are some pluses and minuses, so let's break that down further. Now, for this relationship here, the plus sign would be for when the source is moving away from the observer, and the minus would be when the source is moving towards the observer. And in this relationship, it's the opposite. When the observer is moving away from the source, and when the observer is moving towards, we use the plus sign. Okay, so the hardest thing about this section is simply remembering which formula to use when, and when it's plus and when it's minus. So spend a little bit of time actually learning this off by heart. One way to simplify this understanding and remembering when to use what formula is to know at least one of the derivations. So I'll go through one of them. Again, it's not vital that you know it, and you don't even have to work through this section if it becomes a bit of a burden, but it might help you understand which formula is which. Let's think about what's happening in this situation where there is no Doppler shift. In time t, the wave has travelled vt, so vt is this distance from here to here, and that's the total distance travelled by a wave which leaves the source and travels for time t in all directions, but we're just going to consider this direction. Okay, so as a start, we have d equals vt. Similarly, still considering this situation, the wavelength would be equal to that total distance divided by the number of waves that you would get in that time. Okay, so how many waves do we get in that time? Well, if you remember, frequency equals the number of waves divided by t. So if we need to find number of waves, okay, so let me write that properly. So the number of wavelengths that we get would be f times t, the frequencies at the time. Now, we're not looking for the number of waves. We actually want to know the wavelength. Well, the actual length of one wave would be equal to that whole distance there divided by the number of waves emitted. So we just divide these two expressions. The total distance is vt and the number of waves is ft. So that would give us the wavelength. But remember, this is before Doppler shift. Now let's have a look at this situation. So this particular situation is the source moving towards the observer. And as you can see, the waves there are getting kind of squashed up. The wavelength is decreasing. And we're going to come up with an expression for this new wavelength and then the new frequency. So let's go back to what we did here. The distance travelled now by the wave is much less because the source is kind of doing some work for the wavelength. It's kind of moving for it. So the wave doesn't have to travel far. It doesn't get to travel so far. So this distance here has changed. How much has it changed? Well, in the same way that we worked it out using velocity here, we now have the distance is equal to the velocity of the wave times time minus the velocity of the observer times time. Now what's nice about this is if you understand why it's minus, you can understand that this distance is shorter. You can see why that's a minus sign, and that will help you remember the terms in the relationship. Now, we don't need that. We want the wavelength. So now our wavelength is going to be equal to VWT minus V0T over the number of waves, which is still FT. Now note that this wavelength has a dash here, because this is the Doppler shifted wavelength, the new wavelength, also referred to as the received wavelength. Let's simplify this further. And now we have the difference in velocities over f. So that's our term for wavelength. And that's enough, but that's not what's given in the proof. We now need to come up with an expression for frequency. But remember, frequency is velocity, wave velocity over lambda. So now our observed frequency, let me squeeze it in. So if frequency is velocity over wavelength there, then we just have to divide the velocity or the wave speed over all of this, which flips it round and gives us our relationship here, which if we take the frequency out of the brackets will give us the formula in the data booklet. So it's important to think about this derivation because it helps us understand which formula is which. Now we know why this is minus when the source is moving towards the observer. It's easy to picture why, as the source moves away from the observer, this becomes a plus. Now the proof for when the observer moves, you can have a look at on the presentation itself, but practice as many questions as you can before you get into that. It's not vital, it's not something you need to know. Again, it might help you conceptualize what's going on, but I would do a practice and I would really understand how to use the relationship first, because the questions won't be that challenging. So there is an exception to all this. Waves all exhibit the Doppler effect. However, when we're dealing with electromagnetic waves, there is a bit of a complication. The perceived speed of the electromagnetic waves is unaffected by the speed of the observer. The tail end of this is that you use a different relationship, and it's quite an easy relationship to look at. But before I go over it, let me explain what is the most basic phenomena associated with electromagnetic spectrum Doppler shifts. Now, redshift is a phenomena encountered in astronomy. The idea is exactly the same. If an object is moving away from the observer, so if you're standing on planet Earth here, you're very large, and you are looking at a distant star, which is emitting light of a specific frequency. Now, usually stars radiate in a peak wavelength, as you know, from the black body radiation. So at time t, you might find that we have a blue radiating light, so something that's giving off a lot of blue, or giving off blue with the greatest intensity. Now, because the universe is expanding, and in fact we know it's expanding because of this phenomena, expanding, this star is actually over time moving away from us. Now, because it's moving away from us, the Doppler shift will show an increased wavelength over time. And in fact, that is exactly what happens. All the stars are red shifting away from us. And we call it redshift because if the wavelength of blue light increases, it shifts towards red. On some occasions, the movement of the star with respect to us is towards us. In that case, we would end up seeing the opposite effect. If they are moving towards us, then the red wavelengths, and it could be red or it could be any wavelength, it blue shifts. That means it becomes shorter. The wavelength becomes actually shorter because the wavelength is decreasing. Now that's the most common example of red and blue shift. The relationship is actually really easy to apply. Our change in frequency that we observe over the frequency of the actual light that's emitted is going to be equal to the ratio of the wavelengths, and it's also going to be equal to the ratio of the speeds of the object. Okay, now remember that the speed of light is always 3 times 10 to the 8. So this simplified relationship can be used when we are dealing with electromagnetic waves.